Hi. In this particular class, what we'll discuss the topic of optimization. And optimization is finding the maximum minimum value from a function, and the values that we find are known as the optimal solution. So, but the process of optimization involve following step. In the first step, you'll be making a large and a clear diagram of the situation provided. So this is a situation which is given below. So for this particular case, what you'll be doing is you'll be making a large and a clear diagram of a situation so that you must be able to decipher the information from the um, diagram correctly, right? So that's the information and that's the diagram. So in the first step, you'll be doing this thing. Although in the question, this is given, but in some question you may not be provided with this particular thing. So you need to come up with this situation. In the second step, you'll be constructing a formula and with the variable that is supposed to be optimized as a subject, you'll be bringing that as a subject. And in the third step, you'll be finding the first derivative and you'll be putting that first derivative as zero and you'll try to find the values of x that make the first derivative as zero. In the fourth step, for each stationary point, you will be using the sign diagram or the second derivative test. See, sign diagram test is the first derivative test. That's an alternate name. We did that in our classes as well. And the second derivative test, we'll be doing that once we finish the first derivative test. That's the part of HL curriculum. So I'll be taking you the second derivative test as well. But in the first phase, I'll complete this utilizing the sign diagram or the first derivative test. And whatever the points you'll get, based on that, you can see whether it's a local maximum or a local minima. And then you identify the optimal solution where it is appropriate. So this is the question that I'm going to solve in front of you, right? So a rectangular cake dish is made by cutting out square from the corners of a 25 centimeter by 40 centimeter rectangular tin plate and then folding the metal to form a container. So this was a metal plate in which has a length of like 40 centimeter and a width of like 25 centimeter. And the square of size X was cut from all these four sides, and these were folded together to make this particular container, right? That's the situation, and we have made a diagram for this thing. So now he's inquiring us that what size of the square must be cut out to produce the cake dish of the maximum volume. So what must be the optimal size of these squares so that when they must be cut out, we achieve the maximum volume of the dish container. So this is the situation. We need to construct this formula. And how do we construct that? Let's just move to the, the whiteboard and let's see how it works. Okay. Okay. So this is now what we wanted to make. This was a situation and in which we have like this particular rectangular plate and we are supposed to cut the square pieces of this particular box. It looks something like this. So this dimension was, say, for example, 40, and this length was x, this length was x. So this is going to be 40 minus 2x if I talk about the updated version of this particular length, because this was the original length, which was 40. And now what we are doing is we are subtracting this x length. So this is going to be 40 minus 2x. Similarly, if I talk about this length, this complete length was 25. Now this length is x and this length is x as well. So the updated version would be 25 minus 2x, right? So this is what the scenario is going to be. Now we are provided with the information that volume is equal to length into width into height or depth, right? So length is now 25 minus 2x, width is 40 minus 2x, and the depth is, or the height is x. So when I multiply, I'll get a function of volume of x. V of x is going to be, I'll be multiplying this 25 minus 2x with this one. So this will yield this number 1000 minus 80x minus 50x. And then it would result in a 40x squared. And I'll multiply that with the x, right? So what I'll get is I'll get a volume of function as 1000x minus 130 x squared plus 40 x to the cube. This is going to be the volume of x function, right? So the problem now we have is that we need to find the interval which actually fits in what now we are supposed to calculate its first derivative. So that is b prime of x is going to be 1000, right? I'm assuming that you are familiar with the concept of derivative. That is 260x and plus 40 times of 3 is 120 x squared. Now we are supposed to put b prime of x as 0. So when I'll do that, right? So this is my v prime of x. I'm supposed to produce that equal to 0. So this is going to be 1000 minus 260 x plus 120 x square is equal to 0. So because that's a quadratic equation, so what I'll get is I'll get two values of x. One, I'll put that in GDC. In exam, you can write it like this. Using GDC, we have x as 50 by 3, which is 16, 2 by 3, which looks something like this, or x is equal to 5. Now the problem is that there are two values of x. Which value we are supposed to utilize? So this is something which is important. So we need to find out the interval for this particular case. So I am now rubbing this particular scenario so that I can find the intervals, right? So for finding the intervals, we need to have the information of this particular case, which is this one. Um, I'll be finding the intervals from this particular equation to see whether this x, if that x length come into this interval, I'll be utilizing, if this length comes into the interval or this length, I'll be utilizing that particular value to find the maximum volume of the dish. So now let's just drop all these things and try to find the interval. So this was the original equation. Volume of x is equal to 40 minus 2x multiplied with 25 minus 2x into x. So either 20 minus 2x must be greater than 0, or 25 minus 2x is greater than 0, or x is greater than equal to 0. So we know the property of inequality. Then when we try to move the negative sign, like minus 2x is greater than minus 40, then I try to move this sign over there. So what I'll have is I'll reverse the inequality sign as well. So this is x is less than 20. This one is minus 2x is greater than minus 25. Again, when I'll move this negative sign onto the other half, this is going to switch the sign of inequality, which is x is greater than 0. So when I plot these intervals onto the number line, this is 0, this is 12.5, and this is 20. So this is going to look something like this. That's the first interval, right? That's the second interval. And then x is greater than 0. So this is going to look. So if I try to figure out the common interval in between these three values into these three things, so this is going to be my common interval. So it means that I'm going to assume the value of x which lies in this particular interval. So the only value that I got from the first derivative, that is v prime of x is equal to 0. I got two values of x. One was 50 by 3 and the other value was this one, 5. So 5 is the only value that comes into this interval, whereas 50 by 33 is equivalent to this particular value, which does not come fits into the interval. So x is equal to 5 is the value that yields the maximum volume for a given equation. So let's just see whether this is true or not. So I'll be performing a sign diagram test over here, because we know that sign diagram is the determinant that tells us about the scenario. So x is equal to 5, I'll be placing that over here. So my v prime of x was this particular thing. So मेरा v prime of x जो था वो किसके equivalent था? That was equivalent to 4 into 3x minus 50. Don't use that. That's the factorized form. You can place the value into this form as well, the initial one, 12x squared minus 260x, and then I have the 1000 over here. So I'll be assuming one value onto this side, that's the left side. Let's say x is equal to 4 to see whether I get a negative or a positive value, because I'm not interested in the value, I'm only interested in the sign. So when I place x is equal to 4 into this particular equation, so what I'll get is I'll get a positive value, which means the function on this particular side is increasing. And similarly, when I put a value, take a value, for example, x is equal to 6, and try to place that into this equation, so I get is a negative value. So in the sign diagram, we discussed initially that when we have a critical or a stationary point, say x is equal to 5, and before 5, the function was increasing, and after that, the function is decreasing, the situation might look something like this. So this point is known as a local maxima, right? So this means that this x is equal to 5 is a local maxima. So in the end, we'll be writing this statement as there is a local maximum when x is equal to 5. You're supposed to write that in examination. This is the global maximum for the given domain. The maximum volume is obtained when x is equal to 5, which means that we need to cut the square 5 centimeter from the corner to achieve the maximum volume. And that's it. That's how you optimize the volume for the given scenario. I hope everything is clear. And if yes, then I'll be moving to the next problem. And I'll try to solve that with the method which is known as second derivative test. If everything is clear, I think I should move to that as well now. Okay, so now what I'll be solving is I'll be solving this particular situation in which what I'll do is I'll try to solve this one utilizing this particular scenario. So the situation is a 4-liter container must have a square base. So the base is square, that's what is given to us. And the vertical sides and an open top. So the top is open, base is squared, and we have vertical side, which looks rectangular to me. And I need to find the economical shape which minimizes the surface area of the material needed. So this particular question I'm going to solve with two methods. The first one is first derivative test. I'm not going to do that because that's the SL part. You will do it on your own and try to see whether you get the similar result from the HL part, which is a second derivative test, right? So I'll try to perform this utilizing the second derivative test, right? So that's the situation. You can pause the video if you just don't see the question again, and try to see how do you solve this particular scenario or the problem, right? So now what I'll be doing is I'll be sharing the screen with you so that you guys maybe I'll be solving this particular stuff, right? Okay, so now you are familiar with the problem. Let's just make a clear diagram of it over here, which should look something like this. So I have this particular stuff which looks something like this, and that contains an open container. That one is an open container, and that's the square base, right? This one is the square base. So it means that if this is the square and the open top, so this looks something like this. So if I'm going to calculate the volume for this particular shape, because they have already, sorry for the interruption, we have already provided with the volume as length into width into depth. We know this thing, and the volume is 4 liter, which means that 4000 milliliter. So the length is, because this dimension is same, so this is x, this one is different, so I'm labeling it as y. So x into depth is y. So this is 4000 is equal to x squared y, right? That's my first equation, where I assume that 1 liter is equal to 1000 centimeter cube, right? That's what I made an assumption over here. So we know that we are supposed to optimize the we are supposed to make a shape that makes this surface the economical one. So we need to optimize the surface area. So we know that area of x is given as this square base that is going to be area of base, right, plus 4 times into side length. Whereas we know that the top is open, so that is why we're not multiplying this with 2. If the top was closed as well, then to calculate the surface area, we were supposed to calculate to multiply the top surface with 2 as well. But that's the area of base. So area of base is equivalent to x squared, right, plus 4x into y. If I look at this particular length, right, that's a rectangle, the one I labeled as 1. So this is x into y. So this is going to be 4x squared plus 4xy, because I have this side, the one, the background, and that's 4. So this is going to 4xy. The problem is that up till now, what I have learned is I have learned to solve the equations that are in single variable form. So this equation is in two variable form, that is x and y. So I need to make sure that this y is converted into x. So this is going to be, so here I can extract y. So from this equation, I can get y as 4000 divided by x squared. So I'm going to substitute this a into this equation, which I'm labeling as 2, right? So this is area of function will get updated as x squared plus 16,000. I'm multiplying these two equations, 16,000 x divided by x squared. So this x will get cancelled out with this x, and ultimately what is left is 16,000 over x. So this is going to be my a of x function, right? Now I am supposed to differentiate this a of x function. I am rubbing this particular stuff so that I can differentiate that easily. So yeah, here we go. A of x is equal to x squared plus 16,000 x to the power of minus 1. That was the function. I'm going to take its first derivative, and that is equal to 2x minus 16,000 x to the power of minus 2, right? I'll put a prime of x as 0, and what I get is I'll get 2x is equal to 16,000 x to the power of minus 2, right? And then I further solve this to calculate the value of x. I'll get x cube is equal to 8,000. What I did is I just simplified this equation. If you have any problem, just let me know. I just simplified this equation, and I get x is equal to, when I take its cube root, x is going to be 20. Acha, see, if you want to do it utilizing the first derivative test, I'm just giving you the hint what you are supposed to do. You're supposed to make a number line, assume a value onto this side, the value of the seed this side, and see. And what the trend you'll be getting is, like, suppose a value of 19 over here, 21 over here. Put this into this equation and see what the, if the function is increasing or decreasing. So because that's minimum, so it is going to make a sign diagram of this one, which this will make it as a minimum point. So you can do that on your own. I'm not going to solve it utilizing the first principle. I'm going to solve that utilizing the second principle of, which is the second derivative test. So now I'll take its second derivative. So this is going to be, this is my equation. So the second derivative of this one is going to be a double prime of x is equal to 2 minus times of minus 2 multiplied with 16,000 x to the power of negative 3. That's going to be my second derivative. So now what I'll do is I'll put a double prime 20 into this particular thing, and see whether I'll get a point or not. So this is going to be 2 plus 32,000 divided by 20 cube. That's 32,000, and this will yield a value of 6. So now if I look at this 6, So we know that when f double prime of x is greater than 0 or it's a positive value, right? So the function is going to be what? It is going to be the concave up. And whenever we have it, this is going to be concave up. And whenever we have this shape, so what we get is we get a local minima at this particular point. So because a double prime of x, when we inputted the value of x into a double prime, we get this value which is 6. So 6 is positive, it means it is going to yield a shape of concave up. So whenever the curve is concave up, we always have a minimum point, and the solution is going to look something like this. So it eventually means that to yield, um, which eventually means that to yield the most economical shape that minimizes the surface area, we need to have that x length as 20. This will help us in calculating the equation. So now we know that x value is 20, right? Now we are supposed to calculate the y value. So we can calculate the y value from the initial assumption. Now I'm rubbing this thing off. So x is 20. So what y value is going to be? Y value is going to be this one. So I'll get y value from this equation, the initial equation that was 4,000 divided by x squared. So this is going to be 4,000 divided by 20 to the square. So y value is going to be what? Y value is going to be 10. So in order to, so I'm now writing the sentence at the end, the economical shape has square base of 20 into 20 centimeter and a height of 10 centimeter. So at the end, what you can do is you can actually plot, draw a curve like this, and you'll be showing it. Okay, this is going to be the square base. This length is supposed to be 20, and this length is supposed to be 10. That's how you'll achieve the most economical shape, right? So that's it for this particular part. I'll try to come up with another example so that we have some substantial examples to solve our problems, and then you can solve that from the book, and I'll give you the practice problem questions as well, right? Okay, students, so now I'm going to solve another question, that is this one. Brenda is designing a cylindrical tin can for a canned food company. The can must have a capacity of 1 liter, which again means that I'm utilizing 1 liter is equal to 1000 centimeter cube. And they must use a little metal as possible. So explain why the height h is given by h is equal to 1000 divided by pi r square centimeter. And that's a problem that utilizes the cylinder. And the volume is given to us and the surface area is given to us. I need to prove this thing. And in the part C, I is supposed to find the dimension of the can that makes area as small as possible. So this is what I'm going to do into the next problem. That's typically a shape that comes into the exam as well. So you need to have a look at this one as well. So let's just get started. Okay. If you can't see the question, you can just pause the video and see the question again from the background. So this is what we have over here. The situation was this one. Volume of can, we know that it is given by pi r square h because the dimensions were provided to us initially. And that says that that's the radius and that's the height. So now we know that the capacity was 1 liter, and 1 liter is equal to 1000 centimeter cube. So this is 1000 is equal to pi r square h. So h is going to be 1000 is equal to pi r square centimeter. So that's what we were supposed to prove in the part A. right? Now we are supposed to calculate the total surface area, or in other words, we are supposed to calculate this a of x ka function. So we know that the surface area of this particular cylinder is always given by 2 times of the area of base. So area of base is pi r square. So because we have this area base and this base, so we'll be multiplying that 2 and plus 2 pi rh, which means that the area of the rectangle that is made inside this particular shape, we'll be multiplying that with the 2. So again, we have a of r equation over here. Let me just write it like this as a of r, not a of x, because but the unusual thing over here is again h. So we need to put this value of h into this equation so that we have area function in terms of r. So this is 2 pi r squared plus 2 pi r multiplied with 1000 into divided by pi r squared. So I'm just canceling this thing each and everything out. So this is going to be 2 pi r squared plus 2000 r to the power of minus 1. So this is going to be the equation of a of r, right? That's how I'll get this thing. Okay, in the part C, he wants us to optimize, now he wants us to perform the optimization problem. So we can do it both ways. We can utilize the second derivative test or the first derivative test as well. So here what I'll be utilizing is I'll be utilizing the sign diagram test to solve this particular equation. You can do the second derivative test on your own. I'm rubbing this thing each and everything. So up till now we have the area of function as a of r is equal to 2 pi r square plus 2000 r to the power of minus 1. So I'll be calculating dA over dr, which is equal to 4 pi minus 2000 r to the power of minus 2. I'll be putting dA over dr is equal to 0. So this is 4 pi is equal to 2000 r to the power of minus 2. And when again I'll solve this thing, what I'll get is, sorry, we just forget to write this thing. This will be 4 pi r, and this is going to be r cube is equal to 2000 divided by 4 pi. If you have any issues, you can just pause the video and see I just rearrange the terms in this particular equation, right? You can just pause the video and see how I did all this stuff. So when I'll solve this thing, r is going to be cube root of 500 divided by pi, right? Which is nearly equal to 5.42, right? Now again, what I'll be doing is I'll be drawing a sign diagram, plotting a sign diagram test. 5.42 I'll keep over here, and I'll see what's the value that's over here and that's over here. So let's say x is equal to 5 on the left side. I'll be putting that into the first derivative. You just do that on your own. You put that value into dA over dr. And similarly, x is equal to 6, the value that onto this side, into this equation. So when you put this value, you will definitely get a negative value onto this side, which means that the function was decreasing onto this particular half. And when you put, so this is going to be the increasing on this particular half. So the total surface area is minimum when r is equal to, because this is looks something like this. So this particular point is known as local minimum. When we were discussing the sign diagram test, we discussed this thing that if before the critical point the function is decreasing and after one it's increasing, so it means that that point is a local minimum. So we are going to have a minimum point at this particular interval. So this point is a local minima. So yes, R is going to be 5.42. So let's just calculate the value of H from the initial equation. So H is equal to 1000 divided by pi and the cube root of 500 divided by pi. This will result in a value of 10.8, right? So in order to, because our initial hypothesis was the dimension of the can, which makes area as small as possible. So we have the value of R, which is making the area as possible, and the value of H is 10.8. We calculated that from the initial equation, the one in the part A. Now in the end, I'm rubbing this thing, and in the end, what we'll do is we'll make a shape of the can like this, and we'll say that in order to have a can which has a dimension of this one, we need to have the length as 10.8 and the radius as that the height as 10.8 and the radius as 5.42 centimeter. This particular shape will give us the dimensions which makes area as small as possible. So yeah, that's I hope that's it for the class, and I'll upload an assignment on ManageBack for you guys so that you guys may get reference of these questions. Or if you want me to solve any other problem, just let me know, or we do that in the next class if you want to. I'll upload the assignment related to the problems as we discussed over here.